for the introduction, and also thanks to the Women Sensor Committee for organizing this event. In my case, I'm going to do this presentation that it's entitled Generating Electricity in Antarctica, the adventure of installing thermoelectric generators in an active volcano. That permitted us to went to Antarctica last January, the 3 people that you can see in the picture, and we installed a device that generated electricity from the heat of the ground. So that's what I'm going to talk about. And although it's the 3 of us going to Antarctica, we are a bigger group. As Silvia has said, I belong to the Thermal and Fluids Engineering Research Group from the Public University of Navarre. It's quite big group with 20 people. Yeah, there's a problem with the mic.
Because of this.
Basically, we do research about thermal engineering. Okay? So heat exchangers, optimization of thermal processes, and also thermoelectricity. That it's the brand of thermal science that permitted us to go to Antarctica. We work in several projects, but this project that allowed us to travel to this unique place was this one that was funded by the Ministry of the Spanish Ministry of Science, that it's called Autonomous Thermoelectric Generators for Volcanic Vigilance. We are all those people working on the project, although it was only David going to Antarctica. It's a project that we are ending now, so next year is going to come to an end. And as you can deduce from the name, what we do is trying to do something in order to improve the volcano vigilance. And why is this important? So the first 2 pictures are of La Palma eruption. And that reminded us that the Earth is active, that earthquakes and volcano eruptions occur, and that we live in living Earth, that some things happen. When La Palma erupted, we realized that we cannot do anything in order to prevent the eruptions to occur. But what we can do is to predict if these eruptions are going to occur or not. In fact, in La Palma eruption, televisions were recording live that the eruption was occurring. Like in the exact moment when the Earth opened, the televisions were there recording what was happening. This permitted, for example, evacuating some people from different places, although in other volcanoes of the world this is not possible, as Semeru volcano in Indonesia. But what is important is that we are able, using different sensors and different things, that we are able to predict if a volcano is going to erupt or not. And that's important. It's also important to do this monitoring of volcanoes when you realize that 10% of the global population lives in less than 100 kilometers of a volcano. So that means 700 people living really close to a volcano. However, if you see how many volcanoes are being monitored, only 30% of all volcanoes in the world are being monitored. And the main problem why this few amount of volcanoes being monitored is because powering the sensors that are needed in order to predict an eruption require energy, and obtaining energy in a volcano is not that easy. Okay, so we are talking about sensors that, for example, measure variations in the ground. So if a volcano is going to erupt, the ground is going to increase in size. Also, the temperature of the ground is going to change. Maybe there are some gas emissions. So geologists do measure all these things, and in order to measure these things, you need energy, normally electrical energy. But you're in a volcano, like big mountain, and like electrical grid doesn't do not freeze the volcano, and that's the problem. Why the reason why only 30% of all the volcanoes in the world are being monitored. How do the geologists normally obtain the energy? They use PV panels. Renewable source, easy to install, and works pretty good in most volcanoes of the world. However, they have a problem. For example, if the volcano is quite high, it's going to snow, and the panels are going to be covered by the snow. Also, if you live or if you have a volcano in really high latitudes, like really up north or really down south, you don't have sun for months. So you need a really big battery if you want to obtain electricity all year round, the same as you do in order to obtain energy during the day, during the night, the battery, or you don't their power supply in order to power those sensors that are necessary in order to predict if the eruptions are going to. And the idea that came was, okay, so you're in a volcano, that it's one of the most evident places of the geothermal heat. All active volcanoes have heat, like the ground is quite hot. So why don't we use this heat in order to generate electricity? And that was the base of the idea that we started working on this back in 2017, more or less. And how are we going to transform the heat from the ground into electricity? Installing a turbine, that it's the normal thing that you use in order to transform heat into electricity, is not possible. That would be a really big thing with a lot of maintenance, moving parts, and you just require a few watts in order to power your sensor. It does not make sense. So we realized that one alternative was using thermoelectricity. Thermoelectricity is a technology that directly converts heat into electricity. It's made of different semiconductors, and it's much easier than a turbine, and does exactly the same, generates electricity from the heat. In fact, this is a technology, it's not new. It's a technology that NASA uses in the space in order to obtain the energy. All the probes and the rovers that NASA sends to the space have these thermoelectric generators in order to obtain their electricity and power the different things that they do. So it's a proven technology. We have another person. So it's a proven technology that it's really robust because it has been working for more than 40 years in, for example, Voyager probes without any maintenance. So it has proven that it's a really robust technology and that it's really useful. Which is the problem of this technology and why we don't see it like really often. The problem that this technology has is that their efficiency is really low. You compare it with other technologies that convert heat into electricity, the efficiency is really low. That's why the people that research about this focus on two different things. So we can some people focus on materials. If you improve the materials, you can improve the efficiency. Or others, as it's our case, try to improve the heat transfer because the greater the temperature difference between the sides of this thermoelectric module, the greater the generation. So if you have like really good heat exchangers, you are going to generate more electricity, and that's what we focus on in our research. You can see that on the left-hand side graph, the greater the temperature difference, the greater the efficiency. But in this case, like we are going to have a temperature difference between the ground and the ambient. That's what we have, and we just need a few watts because the sensor that we are going to use just require a few watts. So this the advantages of thermoelectricity with being a really robust technology are really worth it for us. We started working, I said 2017 was the real prototypes. The idea began in 2015, and the first thing was to choose the heat exchangers that maintain these advantages of thermoelectricity, and we realized that these phase change heat exchangers are the best. I'm not going to explain much about this because that would be super technical. But well, this idea was really useful because we could achieve the temperature of the ground to be really close to the temperature of the hot side of the thermoelectric module and the temperature of the cold side really close to the ambient temperature. In fact, we patented this technology and we have proven it in different places. So we started in the laboratory Then we went to the closest volcano that we have, that it's in Spain, the Leyre volcano in the Canary Island. And also in the Canary Island and in another island, we installed different devices, and we reached in our last installation 400 watts. In order to, you can have a comparison of the size. You can see that these devices are not that big. Like in the picture, you don't have a reference. Here you can see ourselves over there. These devices are not that big. The left one that was in Day was like 45 centimeters high. And on the right-hand side, it was 1 meter high. And the right-hand one was 1 meter high, so they are not that big. For this Antarctica project, we are interested in replicate, like doing something similar to the left-hand side, that it's just generating enough to power the sensor. In the other case, in Lanzarote, they have a lot of heat, and in that case, we really want to have a medium scale installation, and that's why we reached 400 watts. That it's a really big installation. But for sensor, like few watts are enough, and we are going to replicate the one that you have on the left. And that's how the project began back in 2021. And the objectives are this one, basically demonstrate that we can generate electricity from the ground and do it in a really special place, that it's in Antarctica. Because if you are able to do that in Antarctica, you are going to be able to replicate it to any place in the world. And the question that always arises here, why in Antarctica? Like, there are a lot of volcanoes in the world, but why do you want to go to Antarctica? Antarctica, when you think of Antarctica, it's a really cold place. There are not volcanoes there. There are volcanoes there. It's true that it's the coldest continent, the windiest one, but there are volcanoes in there. In fact, these islands over here, you can see that they were formed because of volcanic activity. So there is a ocean ridge that opens over there. The magma from the earth comes up and created this island. There are like, it's an archipelago of different islands. It's called the South Shetland Islands. And we went to one island that it's called Deception Island. Deception Island, it's this island that you have on the left, and you can see that the island itself is the crater of an active volcano. On the right picture, you can see the crater of a volcano, and you can resemble that the shape of Deception Island is in fact the crater of an active volcano. In fact, when you are there, you really quickly realize that you are in an active volcano. You are walking over there, and suddenly from like the beach or like from the ground, some fumaroles comes up, like fumaroles coming up, and when you go really close and measure the temperature is more than 100 degrees, like boiling and cooking in your kitchen, but that happens like in the beach. You have more than 100 degrees. There's also a bit that it's full of fumaroles, like kilometers of, well, maybe like a couple of kilometers full of fumaroles, and you can see all this water vapor coming up. And in other places, we also measure temperature of 60 or 94 degrees Celsius. That it's really impressive, and you realize that you're in an active volcano. The fact that it's an active volcano has also other implications. The last eruption occurred not that long ago. It was in 1970 for volcanic age that's like super soon. And this eruption destroyed an scientific base that was there that belonged to the Chilean government. It was completely destroyed, and they have left the structure in order to remind people that go there that what's up. This is an active volcano, eruptions can occur, and these eruptions can destroy what you have over here. And when you are there, you have like some security. There is an evacuation protocol, and also there is always like a traffic light that states the activity of the volcano. If it's green, everything seems all right. If it's yellow, watch out. There is some movement going on behind. And also if it's orange or red, you need to leave the island. They are able to do this termination of state of the volcanoes. I'm not sure if I can mute this. Like this. So geologists that are in charge of seeing what's the state of the volcano basically they do these two different things. So they measure some different parameters in order to characterize the volcano, how it reacts over the year, how it increases in size, comes down. Sometimes it's even like bigger. The temperature changes, the gases changes, and that's called temporal series. But they can only do that when they are in the area. So basically, they go from December to March and measure a lot of things. But during the winter, they are not able to measure anything because they don't have any. They also measure other parameters that are related with volcano vigilance, and it's in order to determine if the volcano is going to erupt. Again, this mostly happens when people are there. During the winter, it's difficult to obtain energy. So the idea of the project is, okay, have like a battery that never comes to an end because you have the heat, you always have a temperature difference between the ground and the ambient, and you are going to have like a infinite battery to power all your sensors. And before going there is necessary to do a lot of things because you are going to a really special place. So you need to organize what you are going to do, where you are going to go in the island, because there are like special places where there is heat. You need to tell what are you going to do in each of these places, and also in our case, do a lot of tests in the laboratory before going there. So check how the devices are going to be, how we are going to carry them to Antarctica, test how we are going to measure the operation of the devices, pack everything. We are, for example, the next campaign is going to be in February, and we are now packing. So with several months in advance, you need to pack everything you need, every single tool that you are going to use, everything. Like you need a screw, you need to take it with you. You don't have a shop over there in order to carry it, and you need to do like an infinite list of everything you take and put it in boxes. You also need to have a special preparation in the ministry, and also medical checks. Like need to read a lot of documentation about Antarctica, special permissions because some of these areas are protected, and a lot of paperwork in order to achieve this dream of going to Antarctica. And we started the trip in January this year, so I think it was 7th of January. And our first step was traveling from Pamplona to Madrid. You can see our faces that we were really happy in order to go there. We were excited. It was going to be a lifetime experience. But when we arrived to Madrid, we realized that our next flight was canceled. So we had to stay there one night waiting. We decided it was going to be the only bad thing of the trip. And the next day, we were able to finally take a flight to Chile, first to Santiago, and from Santiago to the south of Chile, that it's Punta Arenas. And when we arrived, we were completely exhausted. In Punta Arenas, the tradition before going to Antarctica is that you need to touch the foot of this Indian, this monument. And the tradition says that if you're going to Antarctica and touch this foot before going there, you're going to be super lucky and everything is going to work all right. So that's what we did. Over here, we were quite excited. Everything reminded us to our devices, but there was one thing that we needed to do, and we needed a negative test from COVID, because you cannot take the illness, like the diseases, to Antarctica. So you have like really strict medical restrictions, and if you have a positive test of COVID, you cannot travel. Like even if you are there, you cannot travel to Antarctica with a positive COVID test. The three of us were negative in this COVID test. We were also lucky because the weather was quite good. So the next day we could take another flight, and we took this flight to King George Island. And we were flying. It's a really small plane. We could see these icebergs that really impressive. And it was also impressive to land in this island, because in Antarctica you cannot build anything, so there are no roads, and the plane needs to land in rocks. So that's also quite impressive. Once we arrived to King George Island, we needed to travel to Deception Island, and in order to do so, we took a boat. This boat was from the Bulgarian army, and it was a 10-hour trip, but it took us like a couple of days because the sea was not in really good conditions. And since the sea is really cold, if you fall to the sea, you only have your consciousness during 15 minutes, I think. You need to wear those suits, survival suits, because if you fell down to if you touch the sea, you can die, basically. So those were quite funny to wear, and we were taking a lot of pictures because we look like Bob Esponge. During our trip in the boat, we could see that and realize that we were in Antarctica with all those Antarctica's landscapes, the icebergs, even the frozen sea, because it was quite cold. But we also realized that in some cases, in some islands, there was no snow, and it was quite cold. You can see that picture over there, and it's because this is a volcanic island. This is in fact this Deception Island. It's hot, and that's why the snow melts. We could also see whales, penguins. This iceberg was full of penguins. It cannot be seen in the picture, but it was full of penguins, but they are like super small. And finally, it was our turn to come down from the boat. You go down to a Zodiac. This was a frozen sea, and some of our colleagues left the boat in order to reach one of the Spanish bases. And in our case, because Spain has two different bases, one that it's called Juan Carlos I, and this one that it's called Gabriel de Castilla, that it's in Deception Island, and this was the one we were going to, and we arrived there after like a couple of days in the boat. The base looks like this. People always ask, how is the base? It's made of containers, so that if you have to leave from Antarctica, you just take the containers, and it's like anything has happened over there. The main building is the green one in the middle. That was like the living base, like the living building where we spent most of the time. You can see that we had like a living room. We had some sofas. We had also this was a place where we had breakfast, lunch, and dinner. We were 35 people living in the base. We were 7 rooms, like there were 4 beds per each room, and we also had like a gym in order to get in shape over there. Our routine, that it's like people always ask about the routine, was this one. So we woke up at around 7. At 7:30 was the breakfast, and at 8 we started working. We worked till 2:30. That it was lunchtime, and then again in the afternoon till a very important meeting that we had every day. That it was around 8. That was the meteor report. So people from IMET, that it's a Spanish meteorological agency, were also in Antarctica, and every day they told us what the weather was gonna be the next day. because everything is conditioned by the weather. If it's too windy, or it's going to snow, or it's going to rain, you cannot go outside. So it was very important to have this safety report in order to organize the activities for the next day. And also to have the information of the tides, because depending on the tide, you could take the boat that moves you around the island or not. So this was a really important meeting. Afterwards, all the resources were coordinated. We had dinner at around 8:30 and go to bed at 11. So this was our each day. It didn't matter it was Monday or Saturday or Sunday. Every day the same. Only difference on Sundays we woke up at 8. The rest was exactly the same. And also because you're living like 35 people, you also need to help with the cleaning, and one day you need to stay there cleaning for the rest. If we focus on the project, the activities that we realize can be categorized in 3 different activities. Some of them were done in the base, for example, preparing the devices, assembling them, preparing all the stuff that we needed. We also needed to check where we were going to install the devices, which were the hottest places in the island. The geologists had told us, but we needed to measure and make sure it was a good place for our devices. So we measured the geothermal anomalies in 4 different places, and in 2 of them we installed a device, as you will see soon. But so you can see better what we did. So our first activity was preparing the workshop. So they're contained, but we need to have a place to work and assemble our devices. So our boxes that you have seen before were there in the middle of the island. We were assigned this container, and our first activity was to transform this empty container in a workshop in which we could work on. So we took different material that we had, we assembled that table, and that was gonna be the place where we worked all of the days. This was our first activity that we were really happy with. Even like you can see the boxes were the base of the table, and these are some woods. Next step was assembling the prototypes. So the devices were disassembled, and we needed to like assemble all the devices before going there, and that took like several days. You can see better what we did. So those are the devices. This part over here is the one that goes inside the ground, okay? Here we have the thermoelectric modules, and the heat that it's not transformed into electricity is released to the environment, and we use these heat exchangers. We protect against corrosion with these boxes, and we also add some products. This took several days, and also, so because we're in women, there's also some electronics that we had to assemble as well. That basically what this electronics does is measure how the device behaves, which are the temperatures of the ground, how much you are generating, emitting this information to different places so you can have real-time information. While we were doing this assembly, we also went to different places of the island in order to measure those geothermal anomalies. The first place where we went was this place with Gimal Bay, with this fumarole coming up from the sea that has a temperature of 100, more than 100 degrees. But this was not a good place in order to install a device. Our device was going to be installed in this place that it's called Caliente Hill. It's a quite big place up to a mountain with a lot of anomalies, and we chose the anomaly that we were going to install our prototype, that it's that one. It measured 40 times 60 centimeters and had temperatures up to 94 degrees. And those were going to be our views for the next days, where we had to assembly everything on field. But before the installation, we needed to take all the materials over there. It was 1 hour and a half journey to the place. The first day that we went there in order to begin with installation, we went by boat, basically because we were carrying a really heavy structure. So we had the help of the Spanish army. We used this boat and we took the structure and walked up to the hill because the anomalies are up there. We arrived there and we installed the structure. The prototypes were more sensitive, so we decided to take it walking. I have said it's 1 hour and a half. So we protected them really well, and we walked over there until we reached the place where we had chosen to these devices to be installed. You can see that there's no snow because the ground is quite hot. We made a hole. It's not a really deep hole. It's like 40, 50 centimeters deep, and it was 93 degrees Celsius. Next step was installing the devices. So you can see there are time lapse of a day that we were doing the assembly. Apart from digging in the ground, you need to do some connections, and the result is the one that you can see on the right hand side. We covered everything with ground, and the device is the one that you have in the bottom left. That it's quite similar to what we had designed here at the university with the designs in the computer, and you can see that it's not that big. Like this one is even smaller, it's like 30 centimeters. When you just see a picture of it, it looks like huge, but if you see us, it's like quite small. It's less than your knee height. Regarding the electronics, once the device was there, it was the turn of the electronics. So as I have said, we use these electronics in order to measure the behavior of our devices. So we control the operation point because a thermoelectric module is like a PV panel. It depends what you connect to it. You are going to have a point of operation or not. So we control to have like the maximum power point place. We charge a small battery, a really small one. It's this black thing over here. We measure different variables and we send it through two different things, LoRa to the base and also satellite communication. So once the box was ready in the workshop, we needed to take it over there. And this is an example that the meteor report is not accurate because there the weather changes like really fast. We were told that it's going to be a sunny afternoon, and we arrived there. We had to do all the wiring of the thermocouples, it started to snow. That it was at first like really snow, but then it started like a really snowstorm, and we had to leave. Like we really wanted to stay there. I was taking out my computer because I wanted to check what was happening, but we had to leave and come back another day. After we came back and we installed everything, we could see that the device was working really successfully. We had a temperature of the ground of around 90 degrees. The environment was around 0 or minus something. And we were generating between 4 and 6 watts. That's enough in order to power some sensors. Our electronics was consuming just 10% of that generation. And in order to have an order of magnitude, it's equivalent to have to charge the car of a battery, half of it per day. And we were really happy about the results. It was the first time that these devices were installed in Antarctica. So when we realized that everything was working fine, we celebrated it, of course. But we didn't stop there. That was the main objective of the trip. But we wanted to to see other places of the island in order to see if it was possible to install more devices. And we went by boat to the other part of the island, to Pendulum Cove, that it's this beach with a lot of fumaroles, and also to the highest mountain that it's called Mount Pond. I'm going to start with this mountain. We had to wake up at 5 in the morning. That was 5 in the morning, but it's Antarctica. You have 24 hours of light, basically. We went there because it was the only window where the weather was going to be fine. And we started going up to the hill, like to the mountain, with the help of some militaries. And suddenly you can see that everything is like super snowy, but suddenly you find some holes in the snow, and when you measure the temperature in those holes, you realize that the temperature is more than 80 degrees. That's why the snow is melting, because the ground is 84 degrees. There are some small areas or bigger areas, as this one in the picture. You can also realize that there is heat because there are these microorganisms that live where the fumaroles are. So if you see some green things in the ground, that means that there is a fumarole over there, and there's it's a hot place. Since we were there, we measured the anomalies. This year, our colleagues are going to install devices in this mountain, but we also wanted to go to the top, and we discovered these ice formations that were really, really impressive. And afterwards, we came down. When we reached the top, that it's this picture, it was completely foggy. Nothing, we couldn't see anything. It was time to go down. And you can see that it was quite cold because my braces were completely frozen. In the other places, the place that it's Pendulum Cove, this beach with fumaroles, we realized that it was not only hot, the sun, but also the water. In the sun, we measured temperatures of around 40 degrees. And in the water, when you measure the temperature of the sun that it's in the water, we reach temperatures of 60 degrees. We were really impressed. So between 40 and 60 degrees. And it was not planned, but since we had more prototypes than what we had installed in the other place, and we had time, we decided to install one of these devices over here. So it was going to be a really special device because it was going to be installed in an intertidal place. So that means it was going to be covered by the sea. So we had to go there when we had low tide, made a hole. When you dig, you get water. So it was quite difficult to do the installation over there, but we finally could do it. And you can see here when the generator with the low tide, and on the right-hand side, the generator with high tide, and it was completely cold. This is the first intertidal generator that has been installed, and it also demonstrated that it was possible to generate in this place. Since it was not prepared to be left for months, this one we took it away, and we only left the other one. And in fact, the picture that has been famous of our trip over there is of this scenery. I'm just ending. So we were there 18 days. Some days were conditioned by the meteor and we couldn't go out. Other days we could travel around the island. You can see the summary over there. And what I can say, that was a really intense experience. You're in a unique place where really few people can go. You have these icebergs, you have this frozen sea. It's really impressive to go there. You can also see some animals that are not really common. You can see penguins, seals, even some birds that are quite weird. Elephants, marine elephants. But like, it was a really unique experience to be there, to meet that place. And that picture over there, the last one, is the day that we were leaving, and you can see our faces that we were completely exhausted. It was really intense, working every day from 8 to 11. But we were really satisfied by the work that we had developed over there. The conclusion is that it has been the first time that these devices have been installed in Antarctica, demonstrating that it's possible to generate electricity from the ground with thermoelectric generators, and you can use that electricity to power some sensors and obtain real-time data. If we made some calculations, we can generate around 15 watts per square meters, and in terms of energy, it means like half the battery of a car. It's there. Now, the question, is it working still? It's not working. We lost the communication during the winter. It's necessary to remind that the conditions are really, really harsh. But it's not something bad. We are coming back. We have learned a lot of things. In this February, other colleagues are going, and the challenge is to be able that the next device lasts at least the whole winter. Because if we obtain energy during the winter, that's the thing that is going to be super useful for the geologists in order to have data during the whole year, that it's something that they cannot have nowadays. Also, we are now supplying power to real equipment of the geologists. This first campaign, we were just using the electricity in order to power our electronics, in order to see how it works. But now we are powering real equipment from the geologists. In fact, we are powering a GPS and some thermocouples, and that's going to be useful information for the geologists. And if we are able to demonstrate that this works in Antarctica, the idea is to extrapolate this to other volcanoes in the world. So that was all. Thank you for your attention. You can see here also other pictures. As I have said in the beginning, we are from the Thermal and Fluids Engineering Research Group. The letters are ITF, so every time we have the opportunity, we take pictures with the letters, and this also describes our experience in Antarctica. And now we have time for questions if you have any.
Thank you very much, Leyre. Your talk has been very interesting, very impressive. So, anyone wants to ask any question, curiosity? Well, I would like to ask you, well,
Also
you told us that, well, maybe people online, if you
chat.
want to ask anything, I would like to ask you about, well, you told us that you stayed 18 days there. When did you go? In what month?
It was January.
January. And what about the prototypes? Were they operative until when? Until winter?
Until Antarctic winter, it's July.
July. Okay.
So they were working for
quite a lot.
6 months.
It's impressive. Yeah.
Yeah. The first device that we installed in Teide, it lasted more than 3 years.
Wow.
Without maintenance. But in this case, the conditions are harder.
Yeah.
So yeah, it lasted 6 months. We know why it has it's not sending, and it's electronic thing. It's the model. We have like a microcontroller that decides when it's going to send information and when not. So the clock of the microcontroller has frozen, and so it never wakes up. So if it never wakes up, you don't have the measurements, not the information. Yes. So it's not about the device. We really think that the device is still working. That when they go there next year, they are going to measure the electricity and it's going to be generated. But we are not getting the information, and it's a problem with the electronics. The clock it's something frozen. So it's something about that. We have learned it's not a failure. Like we're doing research. We are not a company. It's still research. We still have another campaign, and they get to continue research because there's still more improvement to do, and we think it's useful for the geologists.
So just because I wonder about the maintenance of this equipment, with the awful conditions, they will suffer a lot.
But even in NASA's devices, they don't have a maintenance and they work for years. So the idea is to extrapolate that.
So they are supposed to be.
Yes. And the problem is with the electronics. So,
so you have learned that some research, no?
Yeah.
Okay.
question. Thank you, Leyre, for your interesting talk. I would like to know if the values that you have obtained during 6 months are really the ones that you were expecting, or
We were surprised about the results because our previous experience was in the Canary Islands. And in the Canary Islands, for example, the ground is always constant. Like you have 80 degrees always, it doesn't matter what happens. Here, the temperature of the ground varies. If it's snowing, if it's raining, like that the snow melts, and you have like variations on the temperature of the ground. If you have less temperature, you are going to generate less. So that was the first surprise. But regarding the generation, we were pretty happy because we were generating more on field than on the laboratory. So that was like a good part. But yeah, we have also learned about the geology of the ground, that even it was something that the geologists weren't sure about why it was happening. So yeah, we have learned many things also with the method.
congratulations.
Also one question. You said that before, it's about the background of the group, because this project it involves many different disciplines, and that could you please tell us about what's your background and the other people in the group are in many different knowledge.
Yeah, we need knowledge of everything. So the knowledge about geology is something that we need help with our universities because we don't have that thing. We have learned during, like, since we started in 2017, we have learned a lot in the Canary Islands, but we have discovered that each volcano is unique. So the part of the geology is something we need to collaborate with other people. Then the thermoelectric part, how to build the devices, it's like the speciality of the group. So all of us know about that. And the new thing was electronics. So in my case, I had like my background is from electronics, but now other people are learning about it because we know how to do the devices. But if you cannot use the electricity that they are generating, it's not going to be useful. And for that, electronics is super important. And we are like doing some research on this, but also like hiring other companies because we don't have all the knowledge about this, and it needs to like you need to have like working these devices with minus temperatures and really harsh conditions. Also, we need to contact other groups, and we are open for collaborating because we are not experts in doing this special electronics that lasts for all this long. We have learned, but we are normally using like commercial things. And we have a question over here. Will the presentation record
Yes.
available?
It's going to be uploaded to YouTube channel from the Spanish section. So yes, it will be available. Here.
Yeah. Yeah, it's going to be. Yeah, hopefully it will be heard.
Yes. Okay, any more questions? No? Okay, so
I will have a question.
we can listen to you. Yes,
Yeah, can you listen me?
yes.
Okay. I'm working a little bit with thermoelectric generators. We have started to work with the last months, and we are more in the side of electronics. And I would like to ask, when you harvest the energy from the thermoelectric generators, do you use some kind of what is called MPPTs to optimize the harvested energy from the electronic point of view?
We have installed, and the problem is that the commercial converters that you find in the shops are normally for solar panels, and the range that they have does not suit our range. So there is only one commercial MPPT that is useful for our range, and we have been working with it, and yeah, it worked successfully, and we are repeating this year with the same MPPT. We also have an MPPT and then a battery charger. So we have that. And we have proof having a battery charger per each MPPT or a unique battery charger with all MPPTs. We have both alternatives, and we have studied both.
Okay. And are you open to collaboration with this part?
Yeah, because we are a bit lost and there are no commercial things. So yeah, we are open for collaborating.
Because we are more working on the electronic side, so maybe.
Yeah, maybe I can write my email here in the chat. And you can and you can write send an email.
Okay. Okay.